Thanks very much for the invitation. I really appreciate it, especially since I'm a year late. I was invited to be here last year, but unfortunately got sick at the last minute and had cancer. So thank you for the second invitation. I'm going to talk about some joint work with Dimitri Billick, Shomi Ma, and Craig Spencer. And this is a new subject for me, so I'm just going to start with an introduction, assuming that it's a new subject for you too. It's actually a classical subject in harmonic analysis and number theory, and it starts with a definition of what it means to have a sequence of numbers, say in the unit interval, be uniformly distributed. So it's uniformly distributed if the actual number that intersects any given interval is the amount that you expect it to be. And so the first n points should have approximately n times the length of the interval. And if the sequence is uniformly distributed, then for all Riemann integrable functions, you actually get an approximation to the integral by taking an average. So in other words, it suffices to test that with characteristic functions. It also suffices to test it with exponential functions, leading to Weyl's criterion for a sequence being uniformly distributed. And if you substitute f to be an arbitrary trigonometric polynomial into this, then that's what makes it the simplest way of showing that the sequence alpha, the fractional part of alpha times an integer, where alpha is irrational, is a uniformly distributed sequence, 0, 1. Okay, so things get interesting when you try to quantify this concept of being uniformly distributed, and that's what the theory of discrepancy is about. So let's take a look at the above limit and ask how fast can this go to 0? So we're going to look at a limit and ask a quantitative question, then it's also natural to form a supremum instead of the limit. So we define the discrepancy of a sequence as the supremum of this quantity, the number of points in the sequence, in the first n points of the sequence intersecting a given interval, minus the number we expect to be there. So this is a concept that depends on the sequence and this parameter n. And van der Korpet's question was, does there exist a sequence for which this discrepancy is uniformly bounded for all n? And that was answered in the negative in the mid-40s by Van Arden and Aaron Best. So Roth gave a geometric formulation of discrepancy in the unit cube. So now we're going to take an n-point distribution and say the unit square. We're going to form the rectangle, the axis parallel rectangle that's anchored at the origin. So now we can index these by a pair of points x1, x2 in the unit square. And we're going to look at the number of points in the distribution that land inside a given rectangle and subtract off the number that we expect to be in there. And that's a quantity that depends on x. And what we're interested in then is, since these are is upper and lower bounds for this discrepancy. Now, Roth introduced this because what he showed was that this was actually that questions about upper and lower bounds for this quantity were equivalent to those for infinite sequences of 0, 1. And so this introduces some geometry into the picture. And what I mean by an upper bound and lower bound is the following. So take an arbitrary n-point distribution in the square and look at this quantity, which is the sup over all rectangles. So this is the sup in x of that quantity. And is there a function that depends on n, which is a lower bound for this? so we expect to have some kind of growth in n because of the negative result of Van Arden-Errant test. And by an upper bound, what I mean is, does there exist an n-point distribution which satisfies, which is low discrepancy in the sense that that supremum, that lower bound is attainable. So one other remark about this: the rectangles here are anchored at the origin, but when you're looking at this upper and lower bounds, that anchoring at the origin doesn't matter. The sign of discrepancy, the quantity that's inside the absolute values, is an additive function. And so it doesn't matter whether your rectangles are anchored at the origin or at axis parallel and located anywhere in the unit square. So that's not an important feature of this definition. Now, numerical approximation of functions uses this concept of discrepancy in the following way. If we want to approximate an integral by its average, then the inequality of Coxma and Lavka says that the error in that approximation is bounded by a quantity that depends on the function, the variation of the function, some quantity involving mixed derivatives of the function, and the discrepancy of the point sequence. The discrepancy being the supremum of that quantity, the overall possible axis sequence. So this gives you an upper bound on the error that you can obtain, and so therefore it becomes important numerically to construct low discrepancy sequences. So when you're approximating integrals numerically, the well-known Monte Carlo method involves selecting points in the unit cube randomly. A quasi-Monte Carlo approximation involves using a low discrepancy sequence, one for which this lower bound is attained. Okay, so let's be very specific about what we mean for a lower bound for a discrepancy. So I'm going to take the discrepancy for a given rectangle, R of x. I'm going to take the sup over all x. I'm going to take the largest possible discrepancy with respect to the class of axis parallel rectangles, and then take the infimum over all possible n-point distributions. And we ask, for a given n, is that bounded, what function is it, what sharp bounds from below can we get for that? And a low discrepancy sequence will be one for which that lower bound is attained. In other words, a sequence will be called a low discrepancy if this supremum for that particular sequence is bounded from above. Okay, so there are sharp bounds in dimension 2, and even in dimensions 3 and above, the sharp lower bounds are not known. There's been some recent work which made some improvements and some epsilons that were quite ingenious, building on work of Joseph Beck, Lacey, and Billick, and Armin Bardashakian showed new bounds for discrepancy in higher dimensions, but I'm going to mostly talk about the two-dimensional case here. Okay, so one might be interested in how you construct low discrepancy sequences. So here's an example in dimension 2 of the low discrepancy sequence. We're going to take an irrational number. We're going to take the fractional part of alpha k. We're going to equally space those along the bottom, k over n. And if that number alpha is badly approximable, a special irrational number, in other words, for all integers p and q, the distance between alpha and the rationals is 1 over q squared, then, which is equivalent to saying that the integers in the continued fraction expansion are uniformly bounded, then this is a low discrepancy sequence. Okay, so just a note on this inequality, it's always possible to approximate an irrational number well by 1 over q squared times some constant. So badly approximable says that this is the best you can do. Okay, here's another low discrepancy sequence, which is pretty curious. So this is the van der Korpit sequence. Take the binary expansion of an integer and then do a bit reversal. So we're going to define for every n, x of n is the coefficients aj reordered. Then this sequence is low discrepancy. It achieves the lowest discrepancy one can achieve for n-point distributions in the square. Okay, so what is low discrepancy in the square for the axis parallel rectangles? So low discrepancy in this case means that the lower bound is log of n, and each of these constructions achieves that lower bound of log n. So we've been focusing on measuring the discrepancy of the distribution in the unit square by means of axis parallel rectangles that are anchored at the origin. But there's other ways of measuring discrepancy. So the research in this area consists of looking at other ways of measuring discrepancy, say in dimension 2 or in low dimensions, using other norms. So we talked about the supremum of something, so we have an L infinity norm of this difference, but we could measure it using other norms. We could also measure discrepancy using other shapes. So let's let A denote a family of shapes with, like the axis parallel rectangles. And we're going to define the discrepancy of an n-point distribution in the unit square relative to the A as the supremum of, so we're going to take the number of points in the distribution that intersect a given shape, subtract off the number we would expect to find, and take the supremum over all shapes in this class. So, I'm going to now talk about a couple of different families you can look at and see what happens in these cases. So I mentioned in the green there this remark that in dimension 2 we know what the sharp bounds are for the discrepancy of n-point distributions, but in dimension 3 that's still not known. This is one conjecture that's out there. There's others. Okay, so dimension 2, axis parallel rectangles. We have a discrepancy of log n, and we can find, there are several ways of finding point distributions which achieve this lower bound. So the lower bound is sharp because there exist these sequences achieving the upper bound. Okay, so let's take a different family of shapes. Let's take the family of rectangles, but let's allow arbitrary rotations. So in this case, the lower bound for the discrepancy is n to the 1/4, and there exist point distributions which almost achieve that. Let's let A be the class of circles. Then the lower bound is n to the 1/4, and the upper bound is almost achieved. Let's let the family be the family of rectangles with finitely many rotations. So now we're not going to allow arbitrary rotations, but any fixed, so just a fixed number of finite rotations. And then the lower bound is log n. Or we could allow convex polygons, but with fixed angles. We're not going to allow the convex polygons to rotate. So we have a fixed number of sides, fixed angles. And again, we get log n. Okay, let's take the class of rectangles that are now axis parallel, and let's divide them in half. And so now we're going to get a family of triangles. So what's the discrepancy with respect to this family of triangles? So since you're not asking any questions, I'll ask you that question. So the intuition might be that you should behave like the rectangles, that it should be log n. Factors n to the 1/4. And what's happening here, what's important here is the fact that even though you're dividing a rectangle in half, because the rectangles can be arbitrary, you're allowing a continuum of angles. And that is the feature that's creating this dichotomy between logarithmic bounds and polynomial bounds. So in other words, the triangles are really closer to the rectangles with arbitrary rotations than the rectangles that are fixed in axis parallel.
Maybe you're going to tell us this in 30 seconds, but I wonder, is the answer always either log or n to the 1/4?
Yeah, so that was the question that we asked and that interested us. So, well, maybe 60 seconds. So before I do, let me just say a few words about lower bounds. So to get lower bounds it's a tricky thing because you're looking at arbitrary endpoint distributions in the plane, and the reasoning is a combination of, well, they generally involve orthogonality and L2 estimates. And so the general idea is something like this, which is Roth's method. We're going to measure. We have a sign discrepancy. We're not going to take the absolute value yet. So we have a discrepancy with respect to a rectangle, which is now measured by some quantity x in the square. And we're just going to use Cauchy-Schwarz to say that the L-infinity norm can be estimated from below by an integral against any L2 function g, normalized. And we're going to hope that for the right choice of g, we can get the lower bound. So for example, if we choose g to be some Haar functions adapted to rectangles instead of to cubes, in other words, just products of Haar functions in each variable separately, and fix their sizes, this will almost do it. It'll pick up actually square root of log n. So you have to be a little more careful and say we don't just want cancellation, we want some higher order cancellation, so we need to take some of these products. And then, if you're not in the axis parallel rectangle situation, but you have a collection of shapes, which is translation invariant, it has some symmetry, then you can use Fourier transform methods to get hold of lower bounds, again, by measuring an L2 norm of discrepancy. And the thing that the Fourier transform does, because of the way you define it, because of the nature of the definition of discrepancy, is that when you take the Fourier transform of the discrepancy, if your shapes are all translations of a fixed shape and dilation, then what you obtain is something that separates the geometry and the counting of the distribution. All right, so I'm not going to say too much more about lower bounds because really the rest of this is about upper bounds. Okay, so in 2 dimensions, so we notice that it seems to be always log n or n to the 1/4, although there is n to the 1/3 if you allow arbitrary convex sets. But somehow for fixed shapes, it was always log n or n to the 1/4. And we were interested really in how does the geometry of these shapes interact with this notion of discrepancy. So let's go back to the axis parallel situation. So there's another construction that gives low discrepancy sets, and it works as follows. Maybe there's too many words there, but let me just explain it like this. So you take a uniform grid in the unit square. That's not a low discrepancy set because there are rather large rectangles that contain no points at all. And so the discrepancy for these rather large rectangles will just be n times the area, and that's not going to give you a log n back. But if you take javelin. Suppose we want to do this for rectangles with finitely many rotations. Well, then if you want to try to adapt this low discrepancy set to that case of finitely many rotations, then it turns out that step one of what you need, there's a couple of things you need, but step one is to take this lattice and rotate it by an angle for which the slopes are badly approximable simultaneously in all those finitely many directions. And so the first question that comes out if you're trying to construct something with low discrepancy is, can you select a collection of angles such that these slopes are all simultaneously badly approximable? And this goes back to an old result of Davenport, which was used in this paper back in 10, who proved that there exists a dense set of angles for which all of those things are simultaneously badly approximable. And so there's actually a it doesn't have to be the tangent function, there's the generalization of two functions that have bounded derivatives. Okay, so what we looked at was an intermediate situation. We asked, okay, so let's take these axis parallel rectangles and allow infinitely many rotations, but let's start with some collection of rotations that look somehow manageable from a geometric point of view and interesting from a harmonic analysis point of view, like the Lacunary directions. So our first step was to say, well, can we simultaneously badly approximate infinitely many Lacunary directions like this? And it doesn't look like that's the case, but you can almost do it. That is, you can find a dense set of alphas for which these are almost badly approximable, and the factor is log q squared. And that looks like a very tight argument, so I don't think that can be improved. But I don't have to do that. And so what this leads to in the case of Lacunary, rotations is an upper bound for is the construction of an endpoint distribution which has this discrepancy, log n q. Then if you look at Lacunary of finite order, you can achieve any power of log. And what do I mean by finite order? Well, order 1 is just Lacunary. Order 2 means that every point in the Lacunary sequence has a Lacunary sequence converging to it. So think of 2 to the minus j plus 3 to the minus k for order 2. And then we can fill in the powers n to the 1/4 down to constants by allowing rotations through a set of certain Minkowski dimensions. So I only have 1 minute, and in that 1 minute I just want to show you how Fourier series come into some of these estimates. So for example, if you want to prove an alpha estimate for discrepancy, then you end up needing to be able to estimate from above Fourier series. Because this is what gives you the bounds for discrepancy. So to be extremely brief, instead of rotating the grid, let's leave the grid fixed and rotate all the rectangles. Then you're looking at rectangles that have, and you've got this grid here. So you're looking at rectangles and you choose the cell size of your grid so that if you have a cell containing a point in the grid that's wholly within the rectangle or wholly outside, then it contributes 0 discrepancy. So the discrepancy then is picked up on the boundary of the rectangle. And then the discrepancy can be estimated using, basically the discrepancy is estimated using a sawtooth function, in which the angles of your rotation appear. And those estimates of the sawtooth function lead by methods that go back to Erdos and Turan to Fourier series estimates like this. And the connection between approximability of these irrationals comes in putting certain irrational numbers into these Fourier series and getting precise estimates out. Okay, so the methodology, this is a Davenport-like result that we proved for Lacanieri of finite order. And this is this type of methodology was developed in a series of papers by Pipher and Chen. Let me just close by saying that we believe that they're sharp. We believe that this is how you're going to fill in these gaps between log n and n to the 1/4, but we're still working on the lower bounds. And thank you very much.
Time for questions.
Question? So the discrepancy can go to 0 arbitrarily slowly, right? Depending on the choice of the sequences in whatever dimension. Is there a way of choosing a family of sets that can approximate suitably Riemann integral functions and get the lower bound as bad?
Well, for sequences in 0, 1, there's a lower bound of log n for the discrepancy.
Right.
And
And
so, I'm sorry, so what was it?
so I was just wondering, can you make the lower bound worse by choosing the geometry of the sets that you're dealing with in higher dimensions?
Okay, so there's a lower bound of log n for all sequences in
And
0,
that
and 0, 1.
can
And then when
factors
you
in-
go to 0, 2, so the connection of sequences in 0, 1, that connection is made through axis parallel rectangles. But then when you start looking at other families of shapes, you don't see anything below log n. Is there a theorem that you're not going to? I don't know, but you don't see anything below log n.
Okay.
Any other question?
Time for a little bit of a few remarks more about the lower bounds. Do you have time?
Okay.
Any remarks about the lower bounds? Tell us a little about lower bounds.
In this case,
In any case you like.
so as I said, in the axis parallel rectangles, what you do is you construct a Haar series that gives you, or rather a least product of Haar series, and so that's the sort of standard estimate. Most of the the lower bounds generally go through L2 estimates, and so that's where the orthogonality comes into play. So for circles, what you're going to do when you take if you take all dilations and translate to the given circle, you're going to use the Fourier transform here in L2 estimate. And this L2 estimate, the Fourier transform of discrepancy, turns out to be a convolution product. So then it just becomes a product of a Fourier transform of the shape and the Fourier transform of this counting point. And so now you get to use estimates on Fourier transforms of circles or Fourier transforms of other shapes. So it's all, and the arguments are pretty subtle, and they can be quite delicate. But I don't really have time to say much more than that. And I don't have lower bounds for this yet. So that's what the next project is.
Let's thank the speaker again.